Hi everyone, and welcome to today's Chemistry Daily Booster. This is number 12 in our Paper 2 series, and it is advanced information listed for those of you doing foundation chemistry. Not explicitly listed on the higher tier chemistry advanced information, but as we know from previous experience, that doesn't mean there won't be questions on this topic. What we're going to look at then is what a reversible reaction actually is to start. When we talk about reversible reactions, these are ones that the products can then react together in order to form those original reactants. So by that, what we mean is they have both a forward and a backward reaction. So whenever we are writing a reversible reaction, we must use this special little symbol as opposed to an arrow. So we won't just write a normal arrow. We would use the half arrow to the right, half arrow to the left, the reversible reaction sign to show that it can go both forwards and backwards. Sometimes they will literally give you a question asking what this means, reversible reaction, or they could ask you what is the symbol used to show a reversible reaction, just draw that little symbol. Now, when we're talking about reversible reactions, if they occur in what we call a closed system, i.e. one where nothing can enter or leave, then it will reach what we refer to as the equilibrium. Now at that point, the forward and backward reactions are happening at the same rate. So what that means as far as the concentrations go, all of those reacting substances are going to have a constant concentration. Be careful with your phrasing here. Do not say that the concentrations of all reacting substances will be the same, because that implies that all of the reactants have exactly the same value as their concentrations. They all have a concentration of 5 moles per decimeter cubed. They don't. They do have a constant concentration though. So whatever their concentration is, doesn't change. So use that word constant rather than the same. We could see a question asking us about dynamic equilibrium. So they could say, what is meant by the phrase dynamic equilibrium? So what we need to say is it's equilibrium because the concentrations of all the reacting substances remain constant and the rates of the forward and backward reactions are equal. So the reason it's dynamic is because we still have those reactions taking place, but because they're happening at that equal rate as one another, then the concentrations of all those substances will remain constant. If we now consider equilibrium position in more detail, when we're actually referring to the equilibrium position, it's a description of the relative amounts of reactants and products at that point of equilibrium. If we describe the equilibrium position as being on the left, then that means we've got a greater concentration of reactants than products. If we describe the equilibrium position as being on the right, then the concentration of reactants is less than the concentration of products. And if we change the conditions, we can actually change where that equilibrium position sits. What we're going to do then is have a look at these different conditions that we can change in order to shift that equilibrium position. So the first one is to do with pressure. So here's our basic rule that we need to learn first of all up the top here. If you increase the pressure, the equilibrium position is going to move in the direction of the fewest moles of gas. So let's have a look at our little example here. This is our balanced symbol equation. Everything is a gas, so we're looking at everything. Now, because we've got a 2 in front of the SO2, there's 2 moles of sulfur dioxide, nothing in front of the oxygen, 1 mole there. So we've got 3 moles of gas on the left and only 2 moles of gas on the right. So if we increase the pressure, the equilibrium position moves in the direction of the fewest moles of gas. It's going to move to the right because that's where the fewest moles of gas are. If you're asked what direction does the equilibrium position move in whatever context, the answer is always going to be either left or right. So even if you're not 100% sure, pick left or right, write it down. Obviously, in this case, if you're asked to explain, you'd have to say to the right, because there are only 2 moles of gas on the right, which are fewer than the 3 on the left. Do we just endlessly increase the pressure then? Well, no. The reason for that is that we quite frequently will have to formulate a compromise between increasing the pressure to move the equilibrium position to the right and making sure that the pressure isn't a problem for us. And the kind of problem I'm referring to here is the cost of the equipment and safety. If we think about generating those high pressures first of all, that's quite expensive to do in terms of equipment to withstand the actual pressure and the energy we need to actually do that, to generate that high pressure. So because of that, it's quite costly. It's also a concern in terms of safety, because if we have things under incredibly high pressures, then there is a risk, if there is a fault in any of the equipment, of quite a serious explosion. So that could obviously be hazardous to people's health and welfare. So what we tend to do is a compromised pressure, high enough to give a reasonable equilibrium yield, but not high enough to be overly expensive or hazardous. Back to number 2, the concentration. If we increase the concentration of a substance, the equilibrium position moves in the direction away from the one that is increasing in concentration. So in our little example here, if we increase the concentration of hydrochloric acid, then the equilibrium position moves to the right, because it moves away from the substance that has the increase in concentration. Third factor, temperature. If we increase the temperature, the equilibrium position moves in the direction of the endothermic change. What you will find in a question that's asking you to use equilibrium position and choosing conditions is that you're going to see next to the balanced equation this little bit called delta H. So this is telling us the energy change involved in the reaction, and that will always be for the forward reaction, so towards the right. In this case, we can see there is a negative sign in front of the 58. So we know that negative, I hope, is an exothermic reaction. So our forward reaction is exothermic in this case. So if we increase the temperature, the equilibrium position is going to move to the left, because that's the direction of the endothermic change. So what we see here is, if they've given you delta H and it's negative, then increasing temperature moves it to the left, because that would be the endothermic reaction. Once more though, we don't just pick the highest or lowest temperature in each case. We will need a compromise for temperature as well, particularly if we're looking at one where it would be shifting the equilibrium position to the left. Because if we shift the equilibrium position too far to the left, what's going to happen is we're going to be making, obviously, a significant amount of the reactants back. We don't want to do that if we want the product. Therefore, you're probably thinking, okay, so let's just drop the temperature right down. However, if the temperature goes too low, then what we're going to find is the rate of reaction is going to slow down. So it's a balance between low enough to give us a reasonable equilibrium yield, but not too low so as to have a very slow rate of reaction. We make a compromise. Quick reminder of those 3 key features. Pressure, towards the fewest moles of gas when we increase it. Increasing concentration moves away from the substance with that increased concentration. And temperature goes in the direction of the endothermic reaction. And remember, an endothermic reaction has a positive energy change. If there are bits you'd like to go through in more detail from today's booster, then obviously use the C5 playlist on the channel. You could also use your revision guide to recap on those key points. And as always, I recommend having a look at some of those past exam questions, just so you're aware of the style of question that comes up. And of course, don't forget to join us once more tomorrow for our next Chemistry Daily Booster.